And we'll start from the current slide. But while that's still coming up, are you planning to graduate from Lawson, or are you just transferring?
Yeah.
So you don't need to know about applying to graduate. And you probably don't have time for this either, but they're looking for note takers for other students and also tutors at both the Space Center and Student Support Services. But you probably don't have time to do either one of those.
I've heard you mention that.
Oh, you have? Okay. All right. Okay. Let me get this then. Sorry I haven't gotten this in grade book because in Blackboard, because I've just been running. Well, and you're welcome to ask me any questions. No, okay. I can't now that we're recording, but I can after class or something once I stop the recorder off. Or I could pause the recorder and go over things with you if you need. Okay. And like I said, I'll give you the second test today. The others if they get here too. Okay, so I think that's all that we got there. Where we are, where we left off last time, was right at the end of chapter 12, 12.5, arc length and curvature, and it's a pretty good summary of what the chapters, the section's been about anyway. Now, this is talking in terms of velocities and acceleration. It doesn't have to be. Any kind of curve that's based on some displacement vector or some position vector, if you, unless otherwise noted, let C be a curve in plane or space. Plane would be if it's two-dimensional, i's and j's only. Space if it's three-dimensional, I, j, and k. I kind of like that this book doesn't go into for space and in space and that kind of stuff. This is bad. I mean, enough as it is. Okay. So here's your position vector in the plane. R of t is equal to some x of t, I plus y of t, j. Okay? Where r is a vector function, x and y are scalar functions, but these are the vectors along that. T is what we call as parameter. If we're dealing with velocity and acceleration, that t is time. But it doesn't have to be time if that's just a parametric equation. Or in space, r of t would be x of t, I, y of t, j, and z of t, k. Again, r of t is a vector function, the bolded vector. These are scalar functions here, but they're directions on, or functions in the direction of those coordinates. Okay, x, y, and z are twice differentiable functions of t. Okay, that's going to be assumed throughout here. Now, again, velocity vector is simply the first derivative of your displacement vector, as always. And everything that follows would be the same as if v was not a velocity vector, but any first derivative vector. Since the velocity vector, the magnitude of your velocity vector would then just be the magnitude of your the first derivative of your displacement vector, and that's what we call the first derivative of that's your speed. Just like in physics, magnitude of velocity is speed. Okay, same thing here. And speed is ds dt. Now, s here stands for distance along an arc or a curve. Okay, not speed. That would have been velocity. But this is ds dt. That's curve arc length. Is what s is, arc length. So ds dt is how fast you're moving along that curve. Your acceleration vector be then the first derivative of your velocity vector, second derivative of your displacement vector, and it has components of, all right, usually we use x, y coordinates, so it's x, y, z, if you go that far, okay? But your acceleration vector, even in free space, okay, you can come up with another orthogonal system to describe this, and this is one is tangent to the vector, and that's the unit tangent vector, which I would have thought they would have already shown you, but it's going to be on the next slide. And the other is the unit normal vector, which always points toward the inside of the curve. Okay, so the tangent vector is tangent to the curve, and the normal vector is perpendicular to that curve, but pointing to the center. So those are perpendicular to each other. Yeah, perpendicular to each other. The component of the acceleration in the direction of the unit tangent vector is your a sub t, where they actually bold this, meaning it's representing the unit tangent vector. And these are unit vectors, by the way, the t and the n. Okay? And this is the component of the acceleration in the direction of the unit normal vector. And its subscript is even bolded because it's referring to that. What is the acceleration of in the tangential direction? That's merely the acceleration due to increase of speed. So it's ds dt, d2s dt squared. Okay? So that's always that component. Now, remember, this is not an easy thing necessarily to get. It's not impossible, it's just the magnitude of the velocity vector. So once you get that in terms of t, then take another derivative of it, and you've got the acceleration component in the direction of the unit tangent vector. Now, I think you may have heard me say before, every other book I've ever taught from calls this kappa. This book calls it k, which is fine. Just say that, capital K. And then that is, the capital K is the curvature times the ds, the speed squared in the normal vector. Okay? Curvature is going to point you in that direction, and then curvature is a magnitude, the ds dt, but that would be in that direction. So, all right. Now let's go back and get some of the definitions for those earlier vectors. The unit tangent vector, remember, if you're traveling on a curve, your derivative is going to point, is going to relate to the speed, it's going to relate to your velocity, it's definitely going to be your velocity vector. That's always going to be tangent to the curve at that point. So if the first derivative of your displacement vector or your velocity vector is tangent, then make it a unit vector, just divide by its magnitude, which again they call the speed, s. The unit normal vector is then somewhat the same pattern here. You take the unit tangent vector, take a derivative of it, and then divide by its. Because just because that's a unit tangent vector, its first derivative is not necessarily a unit vector. Because that can be any size. So divide by its magnitude, and you get the that then is the definition of unit normal vector. Now, again, a unit vector is one of magnitude 1, so if you take a vector and divide it by its magnitude, that's going to give you magnitude 1. Always. Dividing a vector by its magnitude, it will be a vector of magnitude 1. All right, now let's go back to those acceleration unit, the acceleration in the direction of the unit tangent vector. Remember they said that was ds, d2s, dt squared. That's what they had on the previous slide. One easy way to get that is your acceleration vector dot product with the unit tangent vector. Okay? In other words, the total acceleration vector is going to be whatever it is. Get that in the direction of the unit tangent vector, and that then will be the component in the direction of the unit tangent vector. Well, what was this? So that was the first derivative of, well, this is that, okay? And then this, remember, is the velocity vector divided by its magnitude. So why they rearrange the order, I would have did A dot V, dot products are commutative, you could do that. A dot V over magnitude V. This is V, that's magnitude V. So that's simply plugging in that in. And then that happens to be the speed vector. Is the first derivative of the speed vector. Okay? Not speed vector, speed itself. First derivative of the speed. Okay, A sub n, the acceleration normal to the direction, that would be this component, that would be the acceleration in the direction of the unit normal vector, the dot product of those two, These follow just by the definitions almost. What is this? There's nothing very obvious about this that we give it to you. It is the cross product of the velocity times the acceleration, the magnitude of that divided by the magnitude of the velocity. Okay? And again, there's nothing that's really obvious about that. That's a lot of calculations to get to that point, but you can always do it. You're given usually the displacement vector, take the first derivative, that's the velocity vector, take the second derivative, that's the acceleration vector. Then you have to do a cross product of those two, do the magnitude of that cross product divided by the speed. Okay? But far easier than doing that, since this one's so easy to get to, or relatively easy to get to, just the velocity dot with the acceleration, not a cross product, but dot divided. Notice the similarity of these. This is the dot product divided by magnitude of speed, and this is the magnitude of the cross product divided. So they're very similar in form. But the easier way to do this, if you've gone through all this and done all that, you know the acceleration vector already, the total acceleration vector. Find this magnitude, subtract this one that you've just gotten to, which is fairly easy to do from take the square root, because these are Pythagorean, they're perpendicular to each other. So that's usually the easiest way to calculate that normal component. But as from the last slide, that is your curvature times the speed squared, derivative of the speed squared. Okay. Sorry, I said that wrong. The speed squared, derivative of the arc length squared. Okay. All right. I think there's one more slide here. Yeah. And this is the formula for curvature, which I gave way back and didn't give it to you. Now this is in a plane. Don't use this for a spatial curve. Okay, this is only for a plane curve. Okay, what is a plane curve? It's y is equal to f of x. Okay, and take the first derivative, take the second derivative, and then plug those in here. Magnitude of the second derivative. And this is actually absolute value of the second derivative, because this is a scalar function, so this just makes it positive, or even though that value may be negative, it's positive. Divided by 1 plus the first derivative squared, and then to the 3/2 pi. Cube it, and then take the square root of it. Take the square root of it, cube it, whichever works. Now, that wasn't good enough. Oh, and this then is for the silk curve in the plane. If you didn't have y as a function of x, you had a fairly complicated situation. This is just y as a function of x. This is x of t, y is y of t. So you have this in parametric form, not necessarily a function of y as a function of x is going to be a curve like that. Parametric curve could do all sorts of things like this, not be able to be expressed there, but you have two components. So then, the numerator almost looks like a quotient formula, derivative of a quotient, type, a quotient rule type thing. Y prime minus y, x prime y double prime minus y prime x double prime. Okay, and except that's sort of how it looks. That's the only thing. And these are scalar functions, so you just make sure if this thing's greater than that thing, you take the absolute value off. Okay. And then its denominator is very similar to this one, except it's x prime squared plus y prime squared into the 3/2 pi. Okay. Nothing particularly easy about these formulas. Look them up if you need them. Not worth memorizing, in my mind. Okay? Now, if you have a curve, formula for curvature either in a plane or space, this is set up specifically for space, but this could be a plane that this is just r of x and y only. Okay? Now, the very simple looking formula is curvature is the magnitude of your first derivative of your unit tangent vector written as what they call the arc length parameter, or the second derivative of your displacement, magnitude of that, of your arc length parameter. Really simple formulas, but most of the time the arc length parameter is a very difficult thing to define, and getting it in terms of that is not particularly easy. So it's a simple looking formula, but to get there can be very complicated, next to impossible. But when you just have your regular parameter, t, not the arc length parameter, which sometimes is very hard to get, it's a little more complicated formula, but all these things are easy to calculate. If you're given r of t, r prime of t is real easy to get. Just take the derivative. Our double prime is pretty easy to get. Take the second derivative. Cross those together, take the magnitude of that, divide it by the magnitude of the velocity vector cubed. Okay? Ooh, what a pain in the neck. But if you go back from your definitions, you almost see where this comes from. This over this squared, but this is this thing over this squared, and you got the magnitude again, you get the cube. Or, if this is easier for you to do, kappa is the acceleration vector, the acceleration vector, dotted with the unit normal vector, okay, and that would give you the total acceleration in the direction of the unit normal vector, which always points to the interior, so that gives you, and this, by the way, a dot product is a scalar quantity divided by the velocity squared. And usually this is the easiest one to do, unless they happen to give you the unit normal vector. If they do, then this is far easier to do. Okay, remembering that this is the same as that. Okay, these are magnitude, dot product makes that a magnitude. So there's nothing really to tie these together all that simply. But the cross product formulas apply only if it occurs in space. We don't use this rendition when we're talking about a plane curve, okay? Because a cross product in a two-dimensional vector is, it usually doesn't give you very much, so that only applies in space. So that's the very last, I think, slide in the section. Yeah. Now, this is not so much for your benefit, but anyone listening at home. I think I gave all these assignments last time, but just in case you missed them, any of the odds, this is in 12.5, starting on page 864, any of the odds 3 through 9. Now, are you familiar enough with the book to know what I'm talking about? Calc Chat and Calc View. Okay, got it. Okay. They're all at Calc Chat. Okay? And they all, by the way, have answers. The odds have answers in the back too. But Calc Chat does a fuller description of how you get there. Calc View even expands that further, but not all of them. Only usually no more than one per section per group will have that. For instance, 11 through 15, all those odds are at Calc Chat. Only 13 is at Calc View. 17 would be a good one to do. That's at Calc Chat. Either 19 or 21 or both. They're both at Calc Chat. 21's at Calc View. Any of the odds 23 to 27, they're all at Calc Chat. Any of the odds 29 through 35, they're all at Calc Chat. 33's at Calc View. Either 37 or 39, they're both at Calc Chat. Any of the odds 41 to 47, they're all at Calc Chat. 43's at Calc View. Any of the odds 49 to 53, they're all at Calc Chat. Any of the odds, either 55 or 57, they're both at Calc Chat. There's an exploring concepts at 59. It should be at Calc Chat. There's an investigation type problem, 61, and another at 63 you can choose to do, and then something else at 65.
You can do any of those or none of those if you want, but they're all at Calc Chat, or should be. There's a center of curvature problem, 67. Another 69. Well, let's see. I'll just say any of the odds, 67 through 71. They're all at Calc Chat. Then 73 is another in polar coordinates at Calc Chat. And then any of the odds, 75, which is a proof, which you don't have to do, but you can if you want to, through 81. They're all at Calc Chat. There's a couple of true false, 83 and 85. They should be at Calc Chat. And then there's an application, and this is Kepler's laws. I think they mentioned them somewhere earlier in the text. But the trouble is I'm teaching so many different courses, and some of them have done more with Kepler's laws, and some have. I don't remember if it's been in ours or not. But anyway, any of the odds, 87 through 93. A couple of those are proofs. In fact, 3 of them at least, 4 of them are proofs. You don't have to do the proofs if you don't want to, but if you want to, you can check it out at calcchat.com to see if you're doing it right. Now, if you need a few more exercises to do to help you on the test, now, on these review exercises, I think all the answers are in the back, but only the worked out solutions of the odds are at Calc Chat. So it still goes by odds. So you can either do them all 1 through 4, or just the odds 1 or 3. The 1 or 3 are at Calc Chat. You can do both 5 and 6 just for answers in the back, or just 5 to use Calc Chat. 7 is at Calc Chat. 9 or 11 are at Calc Chat. 13's at Calc Chat. 15's at Calc Chat. 17's at Calc Chat. 19, 21, 23, 25, 27, either 31 or 33, 35, either 37 or 39, 41, 43, 45, either 47 or 49, 51, 53, either 55 or 57, either 57 or 50 or 61, 63 or 65, 67, and 69 or 71. Then there's a frictional force problem, 73, which is probably not bad. Okay. And then the problem solving, you might find that helpful. You don't have to do that unless you just want to. Those are that. And that finishes chapter 12. Let me go on and give you, pretty sure. Oh, here's sort of a little problem here. Last week when I turned this in to be copied, I didn't realize that the copier was down. Okay? Let's see if I'm deep enough in the stack yet. Yeah, I should be. Oops. Nope. Too deep. Okay, well, I'm getting about right now. Okay, there's my key. Where are the copies she made? They were dim copies. Oh. Didn't go far enough back. Sorry. No, wait. There's test 2 from the earlier version. It shouldn't be this hard to find. Okay. Okay, there's my key. Usually these I think things have just gotten out of order. Let me. Cal 2. Cal 2. I think what I did, I must have gotten mixed up with my Cal 2 papers. There's test 2 here. I may have to go back to my office because they were sitting on top of the stack. They're not anymore. Let's see what this says. Oh, yeah, that's way too deep. I'll bring it to you. Sorry about this. I hope I no. Okay, here's where Cal 3 begins. That's the research paper. There's your test. Per test. The key. Test 1. Test 1. Test 1. Test 1. Test 1. Test 1. I've taught this class so many times from so many different books. I've got multiple tests in here. But I keep them just in case I need a question. I found out, oh, that's a lousy question. And this test bank can find one that tests the same thing in another one. This is aggravating to no end. Because I saw them on top this morning because I thought, oh, this lousy copier, because she had to use the backup copier and they just came out really pale. But they migrated somewhere and I can't see where that is. Just make sure they didn't get down in the Math 1, Cal 1 stack. Okay, this is an enormous mystery that I cannot understand how it happened. Here is the key, and usually the test is right in front of it. It's not there, or it's right behind it, and it's not there. So, how it got out of place, I don't know. What I'm going to do is pause the recording because I don't need to keep recording this confusion, and I'm going to run down to my office. What's that? Yeah. Okay. So press any key. Nah, that time it did right. Okay. So let's start chapter 13, which is functions of several variables, which to me is more appropriate for Cal 3. Cal 1 basically was differentiation getting toward integration and how derivatives, that kind of stuff. And Cal 2 was carrying on with integration, techniques of integration, applications of integration, stuff like this. And then it got into some other things like series and sequences and those kinds of things, and a little bit of vector stuff. Well, then it picked up Cal 3 from the vector stuff, and that's what we've been in so far, but we need to get back to the, what to me, real calculus that's doing, but now rather than using single value calculus like we did derivatives, of y is equal to function of x, take derivative with respect to x. And then when you integrate integral of f of x dx, that kind of stuff. Well, now in this, let's get my slide to the current slide. We're going to do functions of several variables and then go back and do differentiations and integrations with functions of several variables, not just one. Now, not just talking about parametric equations, though it could apply to that, talking about in general. So, introduction to functions of several variables. What we're going to do here is understand the notation for a function of several variables. And that's pretty straightforward. Sketch a graph of a function of two variables, all know. That means no better than three-dimensional graphs, and I'll do really lousy on those. Sketch level curves for a function of two variables. This goes back to what we did kind of at the very beginning when we did the quadrant surfaces, the level curves there. So it's going to be somewhat like that. Sketch level surfaces for a function of three variables. Oh my word! You can't even sketch a function of three variables. That requires force space. But you can sketch the level surfaces for those functions of three variables. And we'll use computer graphics, thank you very much, to graph the function of two variables. Okay. And you know what? Oh, this is just this first section. Okay, I was wondering. This is just the beginning. This is one long chapter. 10 sections. We're not going to do all 10, okay? We're going to do this first one, the introduction to it. We're going to do limits, continuity. They always want you to do that. And then the meat of it is partial derivatives and differentials. 13.3 and 13.4. Chain rules for functions of several variables. That goes pretty much. Directional derivatives and gradients. That's getting into some sort of new stuff. Tangent planes and normal lines. Extreme functions of two variables and applications of extremes. So we're not going to do all of those, but we're going to do some. We're just going to leave the Lagrange multipliers completely out, but we'll do some. So let's get going on 13.1, which is this, functions of several variables. We know only the function of a single independent variable. That's all we've done so far. Even when we got into parametric equations, we were still dealt with x of t or y of t and z of t. But now we're going to have, and basically then, your x, y, and z were what you would call sort of intermediate functions. You have dependent function, independent functions, independent variable, dependent variable, but in between you had some intermediate, the parameter here was t, say, or s, or whatever you want to call it. You could have x of t, y of t, z of t. These were, this vector function was a function of three variables, but it was each one of them in a different dimension. So you still were dealing with an individual. And those x's, y's, and z's were functions of a single variable, single independent variable. What we're going to do now is talk about functions whose independent variables are multiple. We haven't done that. We had multiple intermediate variables, but not multiple independent variables. So here's some three examples. The work done by a force, W is equal to F times D, is a function of two variables. The force is completely independent of its displacement, okay? And yet, work is dependent on both of those. So basically, work is the dependent variable. These are both independent variables. The volume of a right circular cylinder, V is equal to pi r squared, that's the area of the base, times the height, that will be the volume of the cylinder. Well, the radius and the height have no special relationship to each other. They're independent of each other. So this is a function of two independent variables. Okay? The volume of a rectangular solid, length times width times height, there's three variables that don't have to have any relationship to each other. You can have a room of this size, a room that will incorporate this room and the next room, or this room and the room below it. The length, width, and height are completely independent of one another. So that would be a dependent variable as a function of three independent variables. Okay? Real life situations. We just haven't dealt with real life any further than single variables. The notation for a function of two or more variables is similar to that for a function of single variables. Here's a couple of examples. Z, the dependent variable now, is a function of both x and y. These are two independent variables. And here's what it could be. For instance, x squared plus xy. Okay? Or in 3 space, actually getting to 4 space, w, dependent variable, is a function now of 3 dimensions. Okay? X, y, and z. Okay? 3 variables. And that can be x plus 2y minus 3z. So, a definition of a function of 2 variables, and I think what I want to keep saying is independent variables. We've already dealt with some with 2 variables, but these are independent variables. Let D be a set of ordered pairs of real numbers. Ordered pairs of real numbers. If to each ordered pair, x, y, in that set that you have, there corresponds a unique real value f of x, y, it could be your z if you wanted to call it that, then z is a function of x and y. Not a function just of x, not a function just of y, but of independently x and y. The set D is called the domain. So now you've got a set of ordered pairs. Now think of it this way. Think of that being the x-axis, this being the y-axis, okay, perpendicular to each other. So the floor is now our potential domain, okay? Or some area of the floor defined by some values of x and some values of y. That's our domain. Whereas before, x was our domain, the horizontal axis represented the domain. Now, the horizontal surface represents our domain, okay? Some combination of x and y. And then the function depends on the value x and y, not separately, well, sort of separately, but independent of each other. So this depends on what that ordered pair is down here, but it isn't on one or the other. It's of both. Okay. The range in f is all the values f can take on. If you go like this, you know whatever it wants to do up here above this. But any point z here, or alpha of xy, there's only one that corresponds to that xy point. You can't have one here and one here. That would not be a function. Just like it. A function like that would not have been a relation like that in 2 space would not have been a function. The set D is the domain, and the range is the set of values, alpha of xy, or the z values. Okay. So before, when I teach pre-calculus algebra, I tell them the most important thing to remember is this: y is equal to f of x. If you remember that, you got most of the function stuff down. Now z is equal to f of xy. Z is the independent, is the dependent. X, y are both independent. X, y are called independent variables, and z is the dependent variable. Okay. The trouble is, you could have a whole string of independent and one dependent. Okay. So, it says find the domain of each of these functions. Here's f is a function of xy. So what is the domain of each of these functions? Well, let's do the A one first. What's the thing that bothers you about that, or would be the greatest concern? There's actually 2 of them in here.
If we have y squared underneath the radical.
Okay, what's underneath the radical has to be what? Positive. You can't take the square root of a negative number. So the thing under the radical has to be positive. So there's one restriction we have. Okay? So we'll write that down in math speak. And what's under the radical here, let me get my pen set up, okay, is the x squared plus y squared minus 9 has to be greater than or equal to 0. It can be equal to 0, right? Okay? Now, a little shift of terms here, we can easily add 9 to both sides. I don't know if that's what we want to do, but we can do that. And that would give you x squared plus y squared is greater than or equal to 9. Now, what does that describe to you? Anything?
Yeah, it does. Looks like a triangle to me.
Huh?
Oh, circle, okay.
It's a circle of radius 3. X squared plus y squared equal r squared. That's the circle. Okay? Of radius 3. So r would be 3. 3 squared is 9. So this would be anything greater than that, which means if you had the circle, I usually draw the circle first and then tick off my points because I have trouble hitting these. That's a pretty lousy circle, but you got it. Anything greater than that, equal to that would be the circle itself. Anything greater than that would be a sunshine. No, it would be anything outside the circle. Anything in here wouldn't work. Like 0, 0 won't work because that would be 0 plus 0, 0 minus 9. You can't do it. Okay? So it would have to be anything on or outside the circle. Okay? So that would be your domain of that. There's one other little issue, and that would be x can't be 0 because you can never divide by 0. So now we've got, where is x equals 0? Your y-axis, okay? That's where x equals 0. So it would only be the things here and the things here. But this, let me just, for want of anything else, let's do that in red, which indicates you can't go there. You can't touch that. Anything on this side and outside the circle, and anything on that side and outside the circle, but also x can't be 0. So it can't be anything on the y-axis. So there's your domain you're fiddling with. This part and that part. Nothing, not the circle, not the interior of the circle. The circle itself is fine, except these 2 points of the circle are not fine. Okay? The circle and anything outside of it, just not on the x-axis, or y-axis. Okay, does that make sense? Okay, how about B? I'm going to go on and erase A if that's okay. Ugly as it is. All right, what does B tell you? What do you notice there? Right, so here you have 9 minus x squared minus y squared minus z squared has to be, because it's under the radical, that's under the radical has to be greater than or equal to 0, right? Except, because this is also in the denominator, it can't be equal to 0. Because you see that whole thing. So you can't have it equal to 0 because that would make your square root of 0 is 0. That can't happen either. So that has to be greater than 0. Well, if you do a little manipulation here, that would tell you, this time let's add x squared and y squared and z squared to both sides of the equation. I didn't mean to put anything there, but my pen hit. Okay. Add x squared plus y squared plus z squared. And what we have now, I'm going to reverse the order if that's okay. Is that all right? X squared plus y squared plus z squared. If I reverse the order, I have to also turn around the directional inequality, is less than 9. What is that describing for you? A sphere. Yeah, because any cross-section area of that is a circle, and that's a sphere, okay? And that's the interior of the sphere of radius 9. Of radius 3. X squared plus y squared plus z squared is equal to r squared
that's the definition of a sphere of radius r. So the r squared here again would be, for some reason we're stuck on 9s and 3s, so the radius would be 3. So this would be the interior of that sphere. Not the sphere itself, because you can't include the thing because that's in the denominator, but your domain would be the interior of the sphere. Nothing outside the sphere can go into this. So G would be some function in some fourth dimension, depending on the sphere here. Okay, so it could be the spikes going out or something. I don't even know how to describe it because I live in 3 space and I can't do 4 space very well at all. In fact, okay, so that the x in the numerator doesn't contribute or diminish or do anything to the domain at all. It's just up there. Okay, but that function then would operate on the interior of that sphere. Okay, so that would be the domain, the interior of the sphere. So let me clear my mess again. And let's see how the book did that. Okay. The A here, the function is defined for all points x, y, such that x is not equal to 0, and that the stuff in the radical has to be greater than or equal to 0. And they've already moved the 9 to the other side, so greater than or equal to 9. Well, greater than or equal to 9 would be everything on and outside the circle of radius 3, but you couldn't include x equals 0, any of the x values of 0 equals 0, so that would eliminate anything that otherwise would be okay, but now not on the y-axis. Okay, so here is how they did it. They didn't use 2 different colors, but they excluded the y-axis for x equals 0, and these points here, they put open circles there, meaning those points are not included. So anything on or outside the sphere this way, on or outside the sphere that way, this can't be on the x-axis and it can't be on the interior. So there's your domain, basically the blue of that first one, which is fairly much what we said. Okay, my picture just wasn't quite as pretty, almost, but not quite. Okay, and then the second one, the function defined for all points such that, and they rearranged it already and left off the equal sign because it was in the denominator, so it can't be equal to 0, it has to be greater than 0, and when you switch it around, that puts this thing. Well, that's the interior of a sphere of radius 3. Domain is a set of all the points lying inside a sphere of radius 3 that is centered at the origin. And that covers it all. Can't be the sphere itself, or it can't be anything outside of that. So it has to be only the interior values. So, functions of several variables can be combined in the same way as the functions of single variables. For instance, you can form the sum, the difference, the product, and the quotient of these functions, as long as you're only dealing with their common domains. So if f has a different domain from g, but they have any points in common, then that's what you're dealing with when you're adding and subtracting, multiplying, and somewhat dividing, except with division. You have the further restriction that even though f and g may have these points in common, if g of xy is ever equal to 0, those xy points also have to be excluded. Okay? So some products and differences, as long as they have some points in common between the two functions, some portions of their domains are in common, then that would work for all these. And these also have to be in common for this, but also excluding any values that make that denominator 0. You cannot form the composite of 2 functions of several variables. You cannot. Good. I didn't like doing composites anyway. You can, however, form the composite of the function g composed with h of xy, where g is a function of a single variable, call it u or something like that, but h is the product, is the function of 2 or more variables. Because you see, what the composite function is g of h of xy, okay? And this can only be a single value because otherwise h would be a function. So therefore g is a single value function, h is a value, a function that's a 2-value function, 2 independent values. Okay? G and H both can't be functions of two or more variables. The G has to be a function of only one. Because H of xy can only be one Z value for every xy pair. Okay. Now, a function that can be written as a sum of functions of the form C x to the m, y to the n, where C is any real number, m and n are non-negative integers. That's called a polynomial function in two variables. Now, actually, back when you were doing polynomial variables, probably back in Math 100, you ran into these and you didn't think twice about it. The exponents had to be positive whole numbers. Okay, so you were fine with them. Now you realize those are actually functions of two variables, and you couldn't do anything else with, like, take derivatives, because we weren't doing that back then. Okay, just combining them. So here's some functions: f of xy. That would be x squared plus y squared minus 2xy plus x plus 2. Weird but true. This has a product form in it. Our g of xy, which is 3xy squared plus x minus 2. Okay. Only new thing here is that now you can have products of the variables as well as having the variables separate. Okay. Now, not that you need to know this at this point, but looking at this part, you would think this would be, you only have two independent variables here, so this would be a plane curve. And you would think this would be a plane curve that possibly is circular in nature, because these, your exponents here, the 2's here, the coefficients are both the same value. But the xy means that you got sort of a twist to it, but with a circle, who cares about a twist? And you have a little bit of displacement in the x direction. Now, you don't need to know that or think about that, but that's what this communicates. Whereas this is kind of like a parabola, because you have a y squared and x is only to the first power. But again, because of the cross product, the parabola, rather than being opening up or opening down, is now kind of like it's opening to the side, but that would then, the G would, you don't have to worry with it. That's kind of what you're describing here. Okay, these are polynomial functions of two variables. A rational function is a quotient of two polynomial functions that could have more than one variable. Okay, similar terminology is used for function of more than two variables. Notice they don't just limit it to 3 now. You could have bunches of them. Just don't ask me to draw any at all. I have trouble even describing them. So now they're going to ask you to draw a graph. And this book, this author loves graphs. Okay. And let me just, while we're here, you do know about the research paper. Yeah, you've asked me about that, right?
Yeah, and I wanted to talk to you after class.
Okay. There is a person mentioned here, Mary Fairfax Somerville, and frankly, I'd never even heard of her before I turned this page just now, but obviously one of the very few women mathematicians from anything before the current past 100 years or so, probably less than 100 years. So she could be a potential paper topic if you were interested in that. Okay. Now, I wish I had turned the page earlier. I'm talking about page, have you got a text? Okay. 13.1, page 872. It says, without using a graphing utility, describe the graph of each of these functions with two variables. Z is equal to x squared plus y squared. What would that be? this is on page 872. Back, I didn't notice this because I haven't flipped the page over. See the little exploration in the side? Great.
Yeah.
Okay. What would be, describe the graph of z is equal to x squared plus y squared? Circle of radius square root of z, if you want to know. Z is equal to x plus y. That would probably be a linear function of some nature. Okay? Because both the x and y have exponents 1. Okay, so that would be a line in 3 space. Okay? Going up like this, something like that. Okay? Z is equal to x squared plus y. Yeah, it basically is a parabolic cylinder, you might say. The x on the xy plane, if this is x, that's y, because you could express y as x squared plus y squared. Probably opening that way, and then z just goes straight up. So think of a parabola here going up and down. Okay, that would be what that would be. So that would be a parabolic cylinder is the best thing I can come up with naming it. Number C, we just did that. D, z is equal to the square root of x squared plus y squared.
That's a triangle.
Actually, the key thing to do with that is square both sides. That makes z squared is equal to x squared plus y squared. Okay? And then if you put everything on one side, that would be x squared plus y squared minus z squared is equal to 0. Right? If you remember back in our quadratic surfaces that we were talking about then, the x squared plus y squared minus z squared is equal to 1, that would be a elliptic hyperboloid of 1 or 2 sheets. Yeah. Anyway, back there with 0, that basically is your cone coming down, because you see x, y, z all equal 0 fit. Okay, when x equals 0, y equals 0, z would have to be 0, and that's the only point that could be there. And then from there you move on out. So I think that's your cone. And then z is equal to the square root of 1 minus x squared plus y squared. Again, the key is to square both sides. The z squared is equal to 1 minus x squared plus y squared. Then if you move the x squared and y squared to the other side, you'd have x squared minus y squared plus z squared is equal to 1. And that would be your hyperboloid of, I think, 2 sheets, I believe. I can't remember for sure, but it's an elliptic hyperboloid, I believe. Unless they don't mention an answer to that question, but that's why we started the section in 12.6, no, 11.6, or whatever it was with we actually started a little before that, but that's the first thing that, or one of the things covered is the quadratic surfaces. Now, just going through, I think we've hit most of the rest of it. Alpha of x, y is equal to x squared plus y squared would be see that equation at the bottom. One thing that hopefully pops out at you your F has to be positive, right? Because X squared is always positive, Y squared is always positive, and the sum of them is always positive. Could be zero, but so in other words, the range of F of X, Y would be greater than or equal to zero. Domain, any real numbers for X's and or Y's. Okay? But the next one, F of X, Y is equal to log of X, Y. What can you tell me about those? The domain. Okay? So two things to keep in mind. You can't take those. Oh, here's Justin. For some reason. Justin, did I give? Let's see, were you here last time? No, you weren't. Yeah, that's right. Nobody was. I thought I had run off my second test, and I can't find it anywhere in it, but her box is full downstairs, and so I have a few that's in her box, and she just didn't get a copy. Okay, thank you. But her office was locked, so I couldn't find out any more than that. Okay. Let me, sorry. But don't do this now. I forget about it later. There we go. Okay. All right, we're on in chapter 13 now, 13.1, on page, right at the bottom of page 872. I've shown more PowerPoints than this. In fact, we've done a couple of the examples, but I hadn't turned the page, so I didn't notice that this was in the bottom. So what we're talking about here, let's do it here. All right. F of xy is equal to the log of xy, natural log of xy. Now, what I was mentioning, what's the domain of that function? Where a domain now is a set of ordered pairs for x and y. And I was calling on you. What do you remember about the log function? There's two really important features of the log function. You cannot take the log of 0. Cannot. The other one is sort of similar. You can't take the log of any negative number. So it's a lot like a square root, except you can't take the square root of 0. Log, you can't take the log of 0 of the negative number. You also can't take the log of 0. So obviously, neither x nor y can be 0. Okay? Now, but x can be negative if y is negative, because the product would be positive, and you can't take the log of the product of positive numbers. Or if x and y are both positive. Okay? So what we're talking about here, the domain for x and y to be positive, that means you're in the first quadrant or the third quadrant, but you can't be on either axis, okay? Because then x or y would be 0. So it's everything colored in on the first quadrant, but not the quadrant, the quadrant itself, either axis, and the third quadrant, but not that. So that would be the domain here. Rather a little bit weird domain. The origin, of course, is not on it because they both be 0. Okay? And what would be the range of that function? All real numbers. Because log can go very negative. If this product here is less than 1, then your range is no, that's not said right. If the
product here is between 0 and 1. Can't be just anything less than 1, between 0 and 1. Can't be 0. It could be 1, but then it would be 0. But anything between 0 and 1, if that product is between 0 and 1, you're a negative number. And anything, the product being greater than 1, a positive number, and 1 is equal to 0. So your log function looks like this. So it can take on the f of xy can go from negative infinity, positive infinity, and everything in between. But the x and y cannot. I think that's all they're asking for there. Yeah, and that's what they say. All points in the first and third quadrants. And they didn't specifically say, but not counting the axes. Okay. And then this is example 1. We've already done that. A and B. And where were we?
We're at the beginning of top of page 7.
Yeah. Okay, I've done that. All right, I think we have done that slide too. Yeah, we were at this one. So we're at page 874. The graph of a function of two variables. Okay, the graph of a function of two variables is a set of all points x, y, z, two variables, x and y independent, z dependent, for which z is equal to f of xy, and xy is in the domain of f. So basically what you got here is your domain is your xy plane down here, and the z is your dependent variable based on that. A graph can be interpreted geometrically as a surface in space. Why a surface? Because it can only have one value for any value in the domain. So it's always going to be a surface. It can't be a closed figure of any nature. It's got to be a surface. Okay? In this figure, note that the graph of z is equal to f of xy is a surface whose projection onto the xy plane is d, which is the domain of f, which is this value. X is going from 0 to some value here, call it a. Y is going from 0 to b. And so it would be the rectangle defined by x equal a here, y is equal to b here, between that and the positive values for x and y. Okay? Now this surface, strange, weird looking little surface, it looks like a tent of some nature, okay, that going up like that, pegged down here at the edges, and some sort of an arc frame there that is holding it up. And this would be your point x, y, z for any x, y in the domain D. The domain now is a surface, an area in the x, y plane. And for any value inside this, not out here or anywhere else, inside of this, there is one and only one value for z. And every one has it.
But not beyond the plane.
Say again?
Not beyond the dome.
Not beyond the dome or inside the dome, it's just the dome, just the surface. Because one and only one value for z, for any xy value for y. Xy value in the domain. Okay. To each point xy in the domain D, now we talk about domains as the letter D, which is a two-dimensional area of your xy plane. It really looks like it's going to rain today. Do you think it is? No? Okay. I didn't leave my windows down, so I'm not worried. Okay. But all last week I was leaving them down. It was so stinking hot. Okay. There corresponds a point xyz on the surface, and conversely, for each point xyz on the surface, it corresponds exactly one point xy in that value D, in the domain D. All right. So here's example 2. Consider this function. F of xy is equal to the square root of 16 minus 4x squared minus y squared. Find the domain and the range of the function. Not unlike what we were doing before,
Let's first talk about what the domain of that function would be. What would be true about it?
Could not be 0.
What's that?
X over Y could not be 0.
X's and Y cannot be 0? Is that what you said? No, there's nothing to keep them from it. What has to be true, the key here is that square root symbol. Okay? And what do we know about anything inside of square root? Got to be positive, or said math-wise, that would be 16 minus 4x squared minus y squared would have to be what? In math speak, in terminology, in symbology. Greater than or equal to 0. Because you can't take the square root of 0. Right? Okay. Now, let's take that inequality and fiddle around with it a little bit. And you tell me if I'm doing something wrong here. I'm going to add, let's just do it, 4x squared, add y squared to both sides. Okay? And that would give me, I'm going to flip it around now, 4x squared plus y squared now has to be less than or equal to 16. Okay. What does that describe for you? Not a circle. Circle, the coefficients have to be the same. This is like a circle, but stretched in one dimension. Say again? Of what? Oval, yes, exactly like an oval. The mathematical name for it is an ellipse. Okay? This would describe an ellipse. Okay? And if you go back, and this wasn't exactly in that earlier, but I tried to talk about it some. This is a weird way to do it, but it certainly works. If you divide everything by 16, okay, that gives you x squared over 4, which is 2 squared, plus y squared over 4 squared is less than or equal to 1. Okay? Now, what that describes for you is this. Okay. X's and y's can take out any value. I swear. I hate trying to draw these things. Okay. Let me try again. Okay? Because I'm going to need a base. And I can't draw isometric well at all. I'm bad enough with this. Okay? That means you go out. This is the x-axis. This is the y-axis. This is the z-axis. Okay? I'm dotting the negative part. Okay? So you go out 2 here. That's going to be the limit there. Here, 4. Here, 2. Here, 4. Okay? So this will be an ellipse of that general. That doesn't look much like an ellipse, but you get the general idea of it. Okay? And then your f of xy is going to be something over the top of that. Okay? It could be, well, let's see. When x is equal to and it's less than or equal to, it's everything inside and including the outside of that ellipse. It's just a really ugly ellipse. Doesn't look like one. Okay. So when x is equal to plus or minus 2, then y would have to be, oh yeah, we got all that in there. Okay. That's all, they're not asking anything else. Just what is the domain? There's your domain. That the domain of this function is the value set of all x, y pairs such that, and you could write this down, about the only way you can do it is what we just had. 4x squared plus y squared is less than or equals 16. Okay, now that
Feels like to me not very satisfying because we're basically saying what we just did. But that's really all we can say. We can't say the set of all x, y pairs such that x is between minus 2 and x between minus 2 and plus 2 and y between minus 4 and plus 4. That would define a rectangle. And you can't, it's not a whole rectangle. These things outside here are not included in the domain. So basically, that's all you can say, I think. I'll wait and see what they say, and I might modify my response. Now it says, describe the range. The second part is, what's the range of this? Any estimate there?
All values equal f of x, f of y, such that 0.
Okay, f of x, y could be 0, and in fact it is here, and here, and there, and there. In fact, basically it is everywhere here. So I'm going to
modify what I was saying earlier. I can almost come, no, I can't.
But, okay. Okay. Well, all I can tell you is, what does this mean? Yeah. Number one is the principal square root, which means principal means positive. Okay? In other words, this thing's always positive. So whatever is up here is in the positive. It can't be negative because that would be a minus square root. Square root symbol implies principal square root, positive square root. So in other words, the z, you can't have anything down here. It's all got to be up here. Whatever it is, it's going to be up there. Okay? I am going to go back and modify what I was saying.
If you say this is z is equal to the square root of 16 minus 4x squared minus y squared, and then square both sides, like I was suggesting before, z squared is equal to 16 minus 4x squared minus y squared, and then move everything to the other side, you get, not everything, but part of it, 4x squared plus y squared plus z squared is equal to 16. And then divide by 16. That would give you x squared over 2 squared plus y squared over 4 squared plus z squared over 4 squared is equal to 1. We know what that is. That is a ellipsoid. Okay, so that's what I kept wanting to suggest it was. I haven't drawn them big enough. Z goes up to plus or minus 4. Okay, I didn't make that a dotted line. So here it's up to plus or minus 4. Oops, I did it poorly, like that, and then it goes down from there. So that's ugly, okay, but that's what it is. That is a half of an ellipsoid. Can't be the bottom half because this is f of x, y, and z is always positive. So it's the bottom half. So you can almost picture it as a weird kind of Quonset hut. It gets
really narrow at both ends, you know. Okay.
Describe the graph. Hopefully I just described it to you. The domain is everything inside or on the ellipse that I drew there, and the range is positive real numbers up to 4. Can't go any higher than 4. I guess I didn't say that. It's the range is the set of all z values such that z is, let me change that slightly. 0 is less than or equal to z is less than or equal to 4. There's the range. And then describe the graph was the top half of an ellipsoid of those dimensions. I didn't do that right. Sorry about that. Yeah, I think it is. Yeah, that's okay. Okay. Their picture looks a lot better than mine, though. Yeah. Okay. Domain is a set of all points lying on or inside the ellipse, x squared over 4 minus y squared plus y squared over 16 is equal to 1. The range of f all values z, f of x, y such that 0 is less than or equal to z is less than or equal to 4. And a point x, y, z on the graph if and only if z is equal to that, meaning, so basically you have upper half of an ellipsoid shown. I'm not sure I would have drawn my ellipsoid with lines coming in like latitude lines or something like that. That's just bizarre. I would have drawn ellipses in along each of the axes. Okay. And that's what they say to do, but they didn't draw it. Okay. All right. Let's delete all my scratch and let's see if they can come up with anything that looks a little bit better. Domain implied by the equation f is the set of all points x, y such that everything inside that radical has to be greater than or equal to 0. And when you do that, that would be first add the xy terms to the other side and then divide by the 16, and that gives you x squared plus y squared. X squared over 4 plus y squared over 16 is less than or equal to 1, so that would be, the equal to would be the ellipse in the xy plane. Major axis on the y-axis, minor axis on the x. 4 plus, minus 4 to plus 4 on the y-axis, minus 2 to plus 2 on the x-axis. Okay, and the range would be all values, and the reason for that is then when you set that equal to z and then square both sides, it becomes just like your y. So z would be 0 to 4 because you're only the top half of that. Okay. A point x, y, z on the graph if and only if z is equal to that, which would be that, which actually, yes, that's the form that we use for an ellipsoid. All pluses, all variables squared, all pluses in between, and then your equal to 1 on the other side. So your coefficients here are your a squared, b squared, c squared. A is 4, a is 2, b is 4, and c is 4. So you have equal thing there. So the y's go, the x's go from minus, boy, I don't like this. You don't see it. There is a, well, maybe you do see it. There is a curve down there. It's hard to see under here. My outlining it is going to make it any easier to see. Something like that. There is the base, that ellipse that's down there, and then these values go up and down to here, and then they go up and down. You know, I'm not drawing well. Okay, making it worse. Okay, should be from one side to the other. Okay, but that's the half of an egg. You know, it's a boiled egg you cut in two, except it's a really fat egg. Okay, upper half of the egg. Okay. Now let's talk about level curves. Second way to visualize a function of two variables is to use a scalar field in which the scalar z is equal to f of xy is assigned to the point xy. A scalar z is assigned to the point xy. Z is some point corresponding that's equal to f of xy. Scalar field can be characterized by level curves, also sometimes called contour lines. Do any of you ever even hear of the sport called
Orienteering.
say again?
Orienteering.
Orienteering, exactly. You have heard of it? Oh wow. I didn't know very many Americans had. We had an Italian kid live with us one summer, and he was really good orienteer. And in fact, he's on the U.S. national team. Yeah, he's quite good. Not compared to European standards, but American standards, he's very good. And are you an orienteer?
I've done it once or twice.
Oh, okay. But yeah, if all you'll give you is, or you have to provide a compass, and they give you a contour map, and they have the points located on the map, and you have to figure out the path to get there in the right order. So yeah, that's what a contour map is. And what those are level curves, all at the same elevation. Your xy here would be horizontal dimensions, x and y this way, and these would be your vertical things. And let's see, your contour lines here look like they're 4 units apart. Oh, these are isobars. Okay, I see now. This is a map of the U.S., North America, basically. Underneath here, there's Mexico, U.S., Canada, parts of it anyway. And these are isobars. This is pressure lines above and below, and what are your pressure? And 1,000 millibars is about, I thought it was the right atmosphere, 1 atmosphere of pressure. But that must not be true because there's high pressure everywhere here. So where is any low? Usually you have lows if you have high. So I may be wrong on 1,000 being 1 atmosphere. I was thinking it was. But anyway, you have a high pressure center here and here, a higher pressure center here, next higher here, very small high pressure here, but no low pressure centers anywhere. So here's 116 centered here, and by the way, in the northern hemisphere, if you have a closed circle here, your winds go clockwise around the high pressure, clockwise around this one. So you could have some problems here because of conflict in here, clockwise around here, clockwise around here, you could have some problems somewhere in there too. In fact, I just don't see how they could all be high pressure areas. You need a low somewhere in there. Maybe this is your low. I don't know. But anyway, you're getting down to 1,000 here, but down here must be a big low or something. I don't know. So rather a strange map. But anyway, that's an example of contour lines. Isobars. On a contour map, those are called isoclines, equal areas of equal elevation. Okay, and then you have you could have isotherms, areas of equal temperatures. You have this is bars pressure. Are there any others you could have? Same volumes, but that would be a really weird. But anyway,
That's what you're talking about. For a real life contour map, that's what you have. But any kind of shape, you can have your level curves. Any areas of equal distance above your domain. Okay. The weather map here, these are called isobars. The prefix iso means same, and this is bars for barometric pressure, isoclines for elevations, isotherms for temperatures. In weather maps for which the curves represent points of equal temperature, these are isotherms, but this is going to be the next slide. So here we have, and this makes sort of sense down here, you have 80s down here, isotherm, 90s here, 20s up here in good old Canada. I guess you can have sort of pointed type things, but they're almost always more rounded than this, I would think. But there's another couple of 20s up there. So this would look, if these are Fahrenheit degrees, this may be coming up pretty soon. I bet you Canada, not going to be too long before they have some temperatures in the 20s like that, if they don't already. And we will still be in the 70s down here, so this could be something like that. So the level curves are called isotherms. Another common use of level curves are representing electrical potential fields, and those would be, goodness gracious, I can't think of the word for that. Equal potential lines. Okay. I was trying to think ISO something, but I guess you could say ISO potentials, equal potential lines. So that everything's at the same electrical potential. All right. Now, this is contour maps. You often show regions of Earth's surface where the level curves represent the height above sea level. This type of map is called a topographic map. So for this mountain here, the bizarre thing here is you have a near vertical face here. I'm trying to see that on this map. Is that it right here? No, this is the dome right here. This is the highest point here. So it's this right here, I guess. Isoclines are so stinking close together, they're almost on top of each other. So this would be, this face here would be that there. But you see, yeah, because it's cut off here. Part of the mountain fell off or something. You don't have a complete circle here because nothing, this would connect to something over there. Okay. So so that is that side. Most of the time they do form, if this was a rounded mountain, then they would circle around that also here, but it's not. They pick up down here somewhere way down there before you find the next isocline. Okay. You don't want to do orienteering up or down that. That you avoid like the plate. Okay. In fact, you avoid all this like the plate. You're not doing mountain climbing. Okay. So don't go on that orienteer. Okay. All right. The contour map depicts the variation in Z with respect to X and Y, the spacing between the level curves. Much space between the level curves indicate that Z is changing very slowly, whereas very little space indicates a very rapid change in Z. Hang on to all these concepts because they're going to come back and help us in the future. Furthermore, to produce a good three-dimensional illusion of a contour map, it's important to choose C values that are evenly spaced. Okay? In other words, that's your often called the contour space. The contours, there's a name for it. I can't think what it's called now. Okay. So, if you had a perfect hemisphere, which this happens to be, square root of x, 64 minus x squared plus y squared. Okay? So in other words, this thing here has to be greater than or equal to 0. So x squared plus y squared is less than or equal to 64, which is 8 squared. So this is a circle of radius 8.
okay? And then because your z squared is over here, it would be x squared plus y squared plus z squared is equal to 64. That's a hemisphere, not a sphere, a hemisphere of radius 8 everywhere, x, y, and z. The reason is the square root here forces it to be just the top half of the hemisphere. So the contour lines for that are all perfect circles. A point right here at 8, and then the contour. Goodness, I can't think of what they call that, but the spacing. There's 1, 2, 3, 4, 5, 6, 7, 8. So it's 1. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8. So the contour spacing is 1. Yeah, and there it is. C is equal to 1, 2, okay. Is it time? Oh, how in the world could that be? Okay. Let's see how far we got. Oh, this was example 3. So I think we finished that okay, didn't we? We didn't actually draw them. There they would be. Okay. Now you see near the top, very slow change. So the wide spacing around that. But then when it goes down almost vertical, right here, they're getting closer and closer together. So those would be the contour lines for that. Evenly spaced. All right, we'll pick up next time. Goodness, I don't even see this. Oh, I see. They're skipping example 4. We'll start with example 4 next time and move on from there. All right, and I'll try to find out where in the world your test is. I don't know where it is. Homework exercises in 13.1. You should be able to do 5 or 7. They're both at calcchat.com. Any of the odds 9 through 19, they're all at CalcChat, 9's at CalcView. You should be able to do any of the odds 21 to 31, they're all at CalcChat, 23's at CalcView. I'm not sure we've done enough to do. Yeah, I think we should be able to do 33. If not, look at CalcChat. It will have that done for you. And then any of the odds 35 to 41. 42 is sort of interesting, but you don't have that to do. And then graphing using technology. If you do have the technology to do it, knock yourself out with 43 or 45. If you don't, you can play around with it a little bit and see if you can conceive of it, but I'm going to leave that up to you. And then I would try to do all of 47 through 50, only the odds 47 and 49 are going to be in the back of the book and at CalcChat, but you should be able to pick out that from looking at those 4 figures. Okay? And try doing 51 to 57. They're all at CalcChat, 51's at CalcView. We'll hold off there. Somewhere around there. All right, good deal. Well, glad the 2 of you were here. It's been really boring talking to myself today, so we'll pick up and go from there. All right, and I've got to find where my test is. I have a feeling that it's in her box, and they must not have gotten the copier fixed last week because it's still sitting in her box. But I didn't see her here today, so maybe she's not here. Maybe she missed Friday too, so I don't know. But I'll have them ready next time, so anytime you want to come by, you can do so. You might listen and make sure I have them next time before you make a trip. But hopefully, I'll wait on thing. Cancel this.